Okay, continuing on physical chemistry, chapter 3, we're starting section 5 now. We're talking about entropy and what it means for reversibility and irreversibility. Now let's start with reversibility. So we've been saying all along that if we don't specify the system, then the system is implied. So delta S is the same thing as delta S system. Now we also know that the universe is just the sum of the system and surroundings. So delta S system plus delta S surroundings is equal to delta S universe. So here's the diagram. Here's our system. We're surrounded by the surroundings. All that together is the universe. And of course, let's say that heat goes between the system and surroundings. Whatever heat goes into the system must have come from the surroundings. And likewise, if any heat goes into the surroundings, they must have come from the system. So we know that the differential of entropy of the universe is equal to the differential of entropy of the system plus the differential of entropy of the surroundings. That can be mathematically expressed as the dq reversible over T for the system is equal to minus the dq reversibility over T for the surroundings. These two q's, they have to be the same. Therefore, they're going to add up to 0. So what this is saying is that for any reversible process, the change in entropy of the universe must be equal to 0. So likewise, we said that the total entropy of the system plus the total entropy of the surroundings is equal to the total entropy of the universe. Now, since delta S for the universe is equal to 0, then of course the total entropy of the universe is constant for any reversible process. But keep in mind, a reversible process is just an idealization that we're using to simplify the math. It doesn't actually exist in real life. Okay, continuing physical chemistry, chapter 3, section 5. We're talking about entropy and what it means for reversible and irreversible processes. We just did it for a reversible process. Now we're going to do an irreversible adiabatic process. Here's our PV diagram. Let's say we have two states, state 1 to state 2. And we're going to go from state 1 to state 2, not continuously and reversibly, but in a finite number of steps. Well, the consequence is that once we get from state 1 to state 2, we can't get back to state 1. It's an irreversible change. But mathematically, we can compare it to a reversible change. Let's say we want to go from 2 back to 1 reversibly then. Well, what we're going to do is almost exactly like the Carnot cycle. We're going to do an adiabatic compression, we're going to do an isothermal compression, and then we're going to do an adiabatic expansion. Now that will get us back to state 1. And remember, since entropy is a state function, that the change in entropy going this way or that way is going to be exactly the same. So at our S2, entropy at state 2 minus entropy at state 1, has got to be equal to the entropy of the system for our irreversible process. Now let's look at these one step at a time. Going from 2 to 3, we said we're doing reversible adiabatic compression. Adiabatic means that Q reversible is equal to 0, and therefore our change in entropy for this segment must be equal to 0. So the entropy here at state 3 must be equal to the entropy when at state 2. Continuing physical chemistry, chapter 3, section 5, we're talking about an irreversible process and how we're going to calculate the change in entropy for that process. Now I showed you this diagram already, how we want to go from state 1 to state 2 irreversibly, and we're going to approximate it by calculating a reversible path that's going to take us through steps 3 and 4. Now remember, step 2 to 3 we said is reversible adiabat, step 3 to 4 is reversible isotherm, and step 4 to 1 is another reversible adiabat. Now, this is a cycle obviously, but this is not a Carnot cycle, because by definition a Carnot cycle is a reversible cycle. This is an irreversible step, therefore this doesn't fit the definition of a Carnot cycle. Also, we're calling this temperature up here the temperature of the heat reservoir for reasons of convenience. Okay, so we talked already about how this step here is the chain had no change in entropy, so the entropy is state 3 is the same as the entropy in state 2. Now in state 3 to 4, we're going to let heat in to maintain the temperature because we're calling that isothermal, remember. But we also need to get the system entropy at state 4 to match the system entropy at point 1. It should be obvious why. If 2 to 3 is adiabatic and it has no change in entropy, then if 4 to 1 is adiabatic, it won't have any change in entropy either. So all our change in entropy is going to be actually in this isotherm here. So we're going to end up with the entropy of state 4 minus the entropy of state 3 is going to be equal to the definite integral from state 3 to state 4 of the reversible heat divided by temperature. It's an isotherm, so we can pull the temperature out. So we get 1 over TR times the integral from state 3 to state 4 of the reversible heat, which of course is just heat. I should have said the differential of the heat. So that's going to be equal to total heat divided by the temperature of our heat reservoir. Now, since this is a cycle, even though it's not the Carnot cycle, any closed cycle, remember, the cyclic integral of the state function, or the differential of the state function actually, is going to be equal to 0. Now, another way to put it though is the sum of the steps. So the differential of state 1 minus state 2 minus state 1 plus the entropy of state 3 minus 2 plus the entropy of 4 minus 3 plus entropy of 1 minus 4, those all have to be added up to 0 also. Now we know that from state 3 to state 2 is equal to 0, or vice versa, and from state 1 to state 4, vice versa, is equal to 0, because those are adiabatic steps. Therefore, it's just the two other steps that have to add up to 0. Therefore, they must be opposites of each other. If heat goes in one, heat comes out the other, or vice versa. So the entropy of state 2 minus the entropy of state 1 has to be equal to minus the reversible heat done from state 3 to 4 divided by the temperature of our heat reservoir. Now, this term could be positive, negative, or 0, just depending on if the heat's coming into the system, going out of the system, or it turns out to not have any heat change at all. So pay attention to the next few slides, because we're going to talk about what does it mean if it's positive, what does it mean if it's negative, and what does it mean if it's equal to 0. Also, if there's any, we're not necessarily talking about real heat here. If there is heat coming out into the system, then that's going to be equal to the work done by the surroundings. Continuing on physical chemistry, chapter 3.5, we talked about what we're going to how the change in entropy then of our closed cycle is going to depend on whatever happens step 3 to 4. And we said, well, it could be positive, negative, or 0. It just depends on if Q is going to be greater than or equal to 0. So let's see what happens with case 1, where Q from state 3 to 4 is greater than 0. Well, that would mean that the minus work has to be greater than 0. Therefore, the work has to be less than 0. Now, this would be nice, but there's an obvious problem. It would violate the second law of thermodynamics, because then you're converting all the heat into work. So, from that, we can rule out that possibility and say, okay, the Q from 3 to 4 must be less than or equal to 0. And therefore, we could say the entropy from state 2 to state 1 is equal to minus Q to 3 to 4 over THR, so that must be greater than or equal to 0. So let's talk about case 2. What if the heat from step 3 to 4 were equal to 0? Well, then the work would be equal to 0. The only problem is that means that we haven't actually done anything. So that would mean step 3 and 4 are really the same step, and we don't really have any cycle at all. So if we're going to rule that out too, because and say that, okay, that the entropy of state 2 minus the entropy of state 1, they can't be equal to 0. Well, the only case left, of course, is case 3, and that's where the Q from 3 to 4 is less than 0. In that case, then the entropy from state 2 to 1 would be greater than 0, and therefore the change in the entropy of the system must be greater than 0. So what we can conclude from this is that the change in entropy of the system must be greater than 0 for any irreversible adiabatic process in a closed system. Now, every closed system is, well, actually, every isolated system is also closed. So if we have an isolated system, the change in entropy of the system it too must also be greater than 0 for an irreversible process. Now remember, if we added the change in entropy of the system plus the change in entropy of the surroundings, that's equal to the change in entropy of the universe, which must be greater than 0 then for an irreversible process for an adiabatic system. Therefore, we can say that for any process, the change in entropy of the universe is greater than or equal to 0. Okay, continuing on physical chemistry, chapter 3, finishing up section 3.5. So we showed before that delta S for the universe is equal to 0 for any reversible process. And delta S of the universe is greater than 0 for any irreversible process. Therefore, delta S of the universe is greater than or equal to 0 for any process, because those are the only two choices, reversible and irreversible. What this means is that we can create entropy, but we cannot destroy entropy. Now, the second law says that dq reversible over t is the differential of a state function S, such that delta S universe is greater than or equal to 0 for any process. And keep in mind, though, that reversible is an idealization for our math. It doesn't exist in real life. An irreversible process is a real process. Now, let's talk about entropy and what it tells us about equilibrium. Let's say we have a system that's not in equilibrium. One side is hotter than the other. T2 is greater than T1. With this, over time, we should expect those two to have the same temperature. Over time, then, we have entropy versus time. We should expect the entropy to continue to increase because this is going to be irreversible. And it's going to keep being irreversible until they're in equilibrium. So in this case, S is going to be maximized when you're at thermal equilibrium. Thermal equilibrium means the two temperatures are the same, remember. So equilibrium is the state of maximum entropy. Now, one thing to keep in mind, though, thermodynamics can't explain how fast we're going to get to equilibrium. It's just going to tell us where equilibrium is. Okay, we're finishing up chapter 3 with section 3.7. We're going to talk a little bit about what is entropy. Now, we learned from the zeroth law about temperature. The temperature is proportional to the average molecular kinetic energy of our system. And in the first law, we learned about internal energy U, and that U is proportional to the total molecular energy of our system. And then the second law, we learned about entropy, S. But what exactly is S? Well, we have a molecular interpretation of entropy. Let's say we have two inert gases together in a system, E and D. And we're going to start with them separated, D on one side of the system, E on one side of the system. We've got a partition. And we're going to remove this partition. Now, at first, of course, you're going to still have D on one side and E on the other side where they were before. This is called our transition state, and it's less probable. We know that they're going to mix together. So as we approach equilibrium, we're going to end up with D and E on both sides of our system. When we're finally done, you would expect them to be completely mixed. And this state is more probable than this state. So what we're saying is this approach to equilibrium with them completely mixed is spontaneous. And what's happening is we're going from a state that's less probable to a state that is more probable. Continuing on physical chemistry, chapter 3, section 7, we're talking about what entropy means at the molecular nature. Let's say we have a box with one helium atom. Well, I told you the helium atom is in the box. So the probability of finding the helium atom in the box somewhere is equal to 1. But let's say we have a partition, we divide the box in half. What would be the probability of finding the helium in this half? That would be 1/2, because it's 1 over 2. Now, what if we have more than one helium atom, though? Let's say we have 2 helium atoms. The probability of finding both of them on this half of the box is 1 over 2 squared. And if we have 3 helium atoms, the probability of finding all 3 of them over here at the same time is 1 over 2 to the third. And if we have 4 helium atoms, the probability of finding all 4 of them over here is 1 over 2 to the fourth. Now let's say we have a whole mole of gas, and we want to know the probability that they all happen to be on the same side of the box at the same time. That would be 1/2 to Avogadro's number. Now, let's just postulate for a minute that entropy then is a function of the probability. Now we're using P for probability now, not for pressure. So that brings up, you have this question then, what exactly is this function of probability that is entropy? Now let's say we have a container here. We're going to divide it into two parts, and it's totally divided in between by a rigid adiabatic impermeable wall. Remember in chapter 1 we defined what these terms mean. Okay, now we know that entropy is a state function. So the entropy of the whole system is the entropy of part 1 and the entropy of part 2. Therefore, our function of the probability of both is equal to the function of the probability of the one plus the probability of the other. The problem is, though, that probability, when you have the probability of two things happening at once, you multiply the probabilities. You don't add them. Continuing on physical chemistry, chapter 3, section 7, we're talking about the molecular nature of entropy. And we showed before how entropies add up, but probabilities multiply. So what we have to do is we're going to use logarithms. Logarithms are functions that we can use that will convert addition to multiplication. So let's say that entropy then is a function of k times the natural log of p for probability plus a. We want to find out what this k and a are. Now we know that since entropy adds up, the entropy function of x times y, state probability of xy, is equal to k ln of xy plus c. So likewise, the f of x is just k ln x plus a, or the g of y is just k ln y plus b. We're just using different letters for the same functions right now. And we're showing how these two together make this one. A, b, and c are all constants. And remember, c has to be equal to a plus b. But k, we know, is going to be the same for all three functions. Now, a, or this constant, cannot be determined by thermodynamics. So that's why thermodynamics can only find changes in entropy, not absolute entropy. But we are going to have to find a way to, we can find k, the value for k. Now let's start out with a system in an unmixed state like we did before. So we're going to have all the D gas molecules on one side and the E gas molecules on the other. And we're going to give it a temperature, pressure, volume, initial entropy, and initial probability. And then we're going to have the same system in a mixed state with D and E molecules all over the place. We're going to have the same temperature, the same pressure, the same volume, but we're going to have entropy at state 2 and the probability of state 2. Now we know that the change in entropy has to be the entropy of state 2 minus the entropy of state 1. And that's going to be equal to k times the natural log of the probability of state 2 plus a, minus k times the natural log of probability of state 1 plus a. And we're saying that these two a's are the same, therefore they're going to cancel out. So delta S is just going to be equal to k times the natural log of the probability of state 2 divided by the probability of state 1. Continuing on physical chemistry, chapter 3, section 7, we're talking more about the molecular entropy and how we're going to calculate changes in entropy. Remember, for now we're using P for probability, not for pressure, and capital N is the number of molecules, not to be confused with lowercase n, which is the number of moles. Okay, so our probability of state 1 would be 1/2 to the number of D molecules times 1/2 to the number of E molecules. I'm talking about the same diagram from the previous slide, obviously. So when you multiply like that, you can add the exponents. So the probability of state 1 is just 1/2 to the power of the number of D molecules plus the number of E molecules, or the total number of molecules. Now, we're going to simplify, and we'll just assume that number of D molecules is equal to the number of E molecules. Now, also, probability of state 2, we're dealing with such a large number, it's going to be almost exactly 1. So we're just going to round for now and say that the probability of state 2 is 1. So delta S then is going to be k times the natural log of 1 over, and then 1/2 to the 2nd. Remember, this is because nd plus ne, we're assuming they're the same, so it's just 2 times either one. That's going to be k times the natural log of 2 to the 2nd power. You can pull out the exponent in front of the natural logarithm and get 2 times nd times k, natural log of 2. We're going to call this equation 1 for now. Okay, and then delta S, we already showed before that is equal to minus r times na times natural log of xa plus nb times the natural log of xb. And again, we're going to simplify by just assuming that Na is equal to Nb. So the number of moles of each is the same. So the mole fraction of each is going to be 1/2. So X, that would come out like this if you don't believe me. Xa is Na over Na plus Nb. So Na would be over 2Na. The Na's cancel out and you just get 1/2. This is just to simplify the math. It'll work out correctly in the end. So delta S, then we have minus r. We're setting, okay, times 2Na times the natural log of xa, or just 2r times the natural log of 2. Okay, oh yeah, because the natural log of 1/2 would be the same as -1. So we're just doing a little algebra there. Equation 2, rule of exponents, logarithms, whatever. Okay, so we have these two equations. By transitivity of equality, we're going to set them equal to each other. So we have 2 capital N of D is times K, natural log of 2, is equal to 2 times R times lowercase n of natural log of 2. Now we drew two different systems, one with A's and B's, one with C's and D's. What we're going to just say then is that A is equal to D. So we're going to rewrite this and just get rid of those 2's, they'll cancel out obviously. So capital N of D times K is equal to capital R times lowercase n of D. So we're going to solve for k, because this is what we were trying to do all along, and we get r times nd over nd. Now remember, capital, or lowercase n is the number of molecules. Right? Well, number of moles, and this is the number of molecules. So if you take the number of moles times Avogadro's constant, and you'll get the number of molecules. So this is equal to 1 over Na. So this simplifies to r over Na. So r is a fundamental constant. Avogadro's number is a constant. So dividing those two, we've actually derived a third fundamental constant.